Absolute value inequalities. An absolute value inequality is an inequality that contains an absolute value expression. Here are two examples including graphs of the solutions. Here we have the absolute value of x is less than or equal to 2. And let's look at this solution here on the graph. Let's pick any number in the blue shaded region and test its value with this inequality. So let's start with the one right in the middle. Let's start with 0. If we input 0, we have the absolute value of 0 is less than or equal to 2, which is 0 is less than or equal to 2, and it's true. Let's pick a negative 1. So the absolute value of negative 1 is less than or equal to 2. Is 1 is less than or equal to 2, which is true. Let's pick something in the middle, like 1.5, a decimal. So we have the absolute value of 1.5 is less than or equal to 2. So 1.5 is less than or equal to 2 makes the value true. So that is the solution set and its graph. Then we have example 2. The absolute value of x is greater than 3. Here it looks a little different. Let's pick numbers in this shaded region. So we have negative 4. So the absolute value of negative 4 is greater than 3. Is 4 is greater than 3 is true. And we have over here, let's pick 5. We have the absolute value of 5 is greater than 3. And 5 is greater than 3 is true as well. So here is an idea of where we're headed and how to get the solutions when we have an inequality. So here, example A, if that is the solution set, what we know about inequalities is that this graph is the same thing as negative 2 is less than or equal to x, which is less than or equal to 2. And B, the absolute value of x is greater than 3. This graph, we know from inequalities, shows that x is less than negative 3 or x is greater than 3. These are compound inequalities. So it seems the solutions to absolute value inequalities are turning into compound inequalities. Now let's take a look at the first example a little bit more. So again, we have this conclusion that the absolute value of x is less than or equal to 2 is implying that negative 2 is less than or equal to x is less than or equal to 2. So remember that we define the absolute value of x as the distance the number x is from the origin. And this explains why negative 2 and 2 are the solutions to the equation the absolute value equals to. So we still have those references of our endpoints. But now it's not equal to, it's an inequality. If we use the distance idea with an inequality, then the solutions to the absolute value of x are less than or equal to 2 are all numbers x, whose distance from the origin is less than or equal to 2. The shaded region above includes all the points then that are within 2 units of the origin. Let's now look at this example B again, where we have this compound or inequality for when the absolute value of x was greater than 3. So again, we use the distance idea. The solutions to the absolute value of x are greater than 3 are all numbers x whose distance from the origin is greater than 3. Interestingly, there are 2 distinct shaded regions that satisfy this condition. The set of numbers to the left of negative 3 and the set of numbers to the right of 3 are greater than 3 units from the origin. So the solution is the set of numbers where we have this OR compound inequality. Let's take a look at some more. Here we have the absolute value of x is less than 5. So which of the following x values are in the solution set? So we need to test the values in the inequality. So negative 7, we have the absolute value of negative 7 is less than 5, means that 7 is less than 5. Well, that's false, so not 1. Then we have negative 2.5. The absolute value of negative 2.5 is less than 5, says that 2.5 is less than 5, which is true. So negative 2.5 would be in the solution set. We have 3.6. Let's do the absolute value of 3.6 is less than 5. So 3.6 is less than 5 is true. So 3, that would be a part of the solution set. 4.9, the absolute value of 4.9 is less than 5. Well, 4.9 is less than 5 is true. So that would be a part of the solution set. And then we have the absolute value of 8.75 is less than 5. Well, 8.75 is less than 5 is false. So that would not be a part of the solution set. So 2, 3, and 4 would be, but 1 and 5 would not. Sketch the graph of the solution set on a number line and writing the solution absolute value of x is less than 5 in another way. Let's remember that we're comparing our absolute value to 5. And we have the distance from 0 from the origin is going to be 5 or negative 5. Now, if it's less than, we need all of the values that have a distance less than 5 from 0. So that's going to give us negative 5 to 5 and everything in between. We don't actually include those points, and it creates the compound inequality. Negative 5 is less than x, which is less than 5. Here's another example one more time just for clarity. Let's look at the absolute value of x is greater than or equal to 2. Let's test our values to see which of these x values are in the solution set. We have the absolute value of negative 3 is greater than or equal to 2. It means that 3 is greater than or equal to 2 is true. So 1 is true. We have the absolute value of negative 1.5 is greater than or equal to 2. So 1.5 is greater than or equal to 2 is false. So that is not in the solution set. We have the absolute value of 0 is greater than or equal to 2. So 0 is greater than or equal to 2 is false. So that is not in the solution set. We have the absolute value of 1.9 is greater than or equal to 2. So 1.9 is greater than or equal to 2 is false. So that is not in the solution set. And we have the absolute value of 2.1 is greater than or equal to 2. So 2.1 is greater than or equal to 2 is true. So 1 and 5 are in the solution set and 2 through 4 are not, just by simply inputting them into the inequality. Now, if we want to sketch the graph of this solution set and write it in another way, we have to look at the inequality and remember that absolute value, we're talking about the distance from 0, or the origin, and here it's 2. So we have to compare negative 2 and 2. And then we need all the value, and we equal negative 2 or 2. We have those values. And then we have to have all the values greater, that have a greater distance. So all the numbers past negative 2 and all the numbers past 2. Creating this number line with all the numbers to the left of negative 2 and all the numbers to the right of 2 and negative 2 and 2, which implies this compound inequality of x is less than or equal to negative 2 or x is greater than or equal to 2. So we have this big idea that the absolute value inequalities, its solution set is going to turn into a compound inequality.